Hi y'all, we are ready to jump into graphing rational functions. So some of this actually shouldn't be new. We should know some of the basic shapes of rational functions. And I just want to start with that as a reminder, but our goal is to get into more complicated rational functions that maybe have variables on the top as well as the bottom, and maybe even have cubic or fourth degree numerators and or denominators. And there's some really interesting bits and pieces when you get into that. So this example, we could definitely do with just transformation. So we'll look at that way first, and then we will look at the new way that we're going to approach these, which is basically using local and global behavior. With this very first example, we would think of starting with the parent function, y equals 1 over x. So that looks like this kind of swoosh in quadrant 1 and 3, and it has a vertical asymptote at x equals 0 that lays right on the y-axis, and a horizontal asymptote at y equals 0 that lies right along the x-axis. And usually I just snag the 2 points 1, 1 and -1. -1 when I'm using transformations on this. You could of course get more. We have a formula. So if x equals 2, we could plug that in and get y equals 1/2. If x equals 1/2, you could plug that in and get y equals 2. This is basically the reciprocal function. Your y value will always be the reciprocal of your x value. But those two are particularly nice, and they'll usually get us a pretty decent rough sketch. Make sure you're labeling and drawing in that dashed line for your asymptote. If I don't know exactly where your asymptote is, and if you don't draw it in, I don't even know for sure that you realize that's what's there. So that's going to be really, really important. Okay, so when I'm looking at this graph, again with a little bit of a review piece here, I see a +3, a -1, and the fact that there's a 2 on top instead of a 1 on top. All of those are not part of the basic function, so we have to look at those as transformations. So there's sometimes more than one way to look at the 2 on the top, but I would say the easy way to look at it is we would have had to multiply this entire basic function by 2 over 1 to get that 2 in the top. So if you're multiplying the whole function by 2, that's vertical stretch by 2. And then the -1, that's attached to my x. So I see a shift to the right one. Remember that any transformations affecting your x values are going to do the opposite of what it looks like. And then the way you'd get that +3 on the end and not inside of the fraction is you'd add it again to the entire function. So that's going to be a shift up. That's affecting your y values. Y's are not opposite, so up 3. Okay, so this actually makes it pretty easy to track where your asymptotes end up. If I shift up 3, my horizontal asymptote will end up at y equals 3. If I shift to the right 1, my vertical asymptote will end up at x equals 1. And notice the vertical stretch just doesn't change those. You always do your shifting last. So if you take the horizontal asymptote and you do a vertical stretch by 2, it's at y equals 0, so that doesn't change at all. If you take the vertical asymptote and stretch by 2, technically, I guess that does change. Every point on that vertical asymptote gets twice as far from the origin, but since that line goes infinitely far to the top and infinitely far to the bottom, it doesn't have any noticeable effect. It's still just an infinitely tall vertical line that goes forever. So this gives us the biggest part of our structure. I know that I don't have any flips going on, so I expect to still see something up here and something down here. And I'll just use the points 1, 1 and -1, -1 to get a little bit more accuracy in that and call it good. It doesn't have to be perfect. So if I take 1, 1, and I'm going to first do my stretch, you always do your shifting last. First do my vertical stretch, it will end up at 1, 2. And then I shift to the right one, it will end up at 2, 2. And then I shift, I'm getting kind of into my graph, but that's okay. Up 3, it will end up at 2, 5. So at 2, 5, I should have a point. And then otherwise, I know I'm still expecting that swoosh shape. It's just been stretched up away from the horizontal asymptote a little bit, so it goes up a little bit higher. And then -1, -1 has to go through those same steps. So I do a vertical stretch. It will become -1, 2. That's doubling my y value. I shift to the right one. It will become 0, 2. And then I shift up 3. I'm sorry, I'm writing these as 2's. They're -2's. And it will become 0, 1. So it goes through 0, 1. And otherwise still kind of maintains that same shape. So it's now, since it moved over, it's going across the y-axis, but then it will approach its horizontal asymptote. So that is how I would graph one of these using transformations. And just so you have it as a reference, we also should know the basic shape of 1 over x squared. It's fairly similar. If you graph these two with technology, you'll see that they don't hit the exact same points. But otherwise are very similar in quadrant 1. The one point that they do both hit is that 1, 1. But you can see that where 1 over x went through 2, 1/2, this graph would go through 2, 1/4 because of the square. So it's a little bit different. Then on the left side of the axis, it's different because the square means we won't get any negative y values. So this is another one that you could use. And again, when you're graphing these, make sure that you tell me exactly where your asymptotes are. There will be definite specific credit assigned to showing those. So that would be the basic shape if you had an x squared in there. Okay, so we know that rational functions can have these vertical asymptotes. I will say they don't always, and that's okay. They tend to have some sort of asymptotic behavior, whether it's horizontal asymptotes or slant asymptotes. But we'll see that global behavior happening. As x's get really, really big, your y's tend to follow certain patterns. We want to be able to go straight to thinking about that instead. So let's go ahead and look at this bottom one. So it's the same function. We expect the same graph. I just want to give you a new way to approach it that will work when we don't have something quite this simple that can be related back to a parent function. So the trick here will be to always have a single fraction, and usually we will just start with a single fraction. You won't have to do the work, but I wanted this one written separately so we could see the transformations. So I would end up with 2 plus 3 times x minus 1 all over x minus 1 if I got a common denominator. So it's 2 plus 3x minus 3, which is 3x minus 1 over x minus 1. Okay, so we want to think about local and global behaviors. So local is going to be zeros, x-intercepts, right? Holes, which we haven't really talked about in detail, but we'll see them. There's not one here, I'll just let you know. And then vertical asymptotes. This one's kind of funny because if your y's go up forever, there's something very global about that, but I'm going to still call it local because I'm thinking about that zoom way in or zoom way out. If you zoom way out, often technology will either completely hide or just like blur the details of the vertical asymptote. So the global is going to be our horizontal asymptote. And again, we will get another option as we work into this. There could be a slant asymptote, sometimes also called an oblique asymptote. That's the same thing. So there's other possible global behavior, but we'll be focused on that horizontal. And what I'm thinking with the global is that the question here is what happens as x gets really, really big or really, really small. That's why I'm calling this global. So with vertical asymptotes, y gets really, really big or really, really small. But x is just getting close to some specific number, like in our previous example, x equals 1. Okay, so to find zeros, this is just some fraction reasoning that happens. To find zeros, what I want you to remember is that the only way to make a fraction equal to 0 is if the top is 0. So for zeros, we want to be thinking this. We're setting the whole thing equal to 0. That's only true if 3x minus 1 equals 0, which means x has to be 1/3. Sorry, smushing a step or two together there just so that we can fit it, but add 1, divide by 3. So we get 1 x-intercept at 1/3, 0. A really, really important thing to realize is that that means that that is the only place you can cross the x-axis. And interestingly, you might hit one that doesn't have an x-intercept at all. That's really helpful information still, because that means you're never allowed to cross the x-axis. Possibly there's a horizontal asymptote there. Holes, we'll get there, but remember that's when the top and the bottom share a factor. So algebraically, you'd want to cancel that out. Graphically, that leaves a single hole in the graph. Vertical asymptotes, this happens when the fraction is undefined. Holes, I guess, technically also happen when the fraction is undefined, but basically vertical asymptotes happen when the bottom is getting really, really close to 0, but the top isn't. So for a vertical asymptote, we would want to know when x minus 1 equals 0, which is when x equals 1. So a vertical asymptote, and it should just be written that way, as x equals, y could be anything, it's a vertical line, x has to equal 1. Okay, global behavior, we're either going to have a horizontal asymptote or a slant asymptote. Should be what we're mostly seeing. I guess actually you might see one occasionally that has a hole and doesn't have a horizontal or slant asymptote, but typically we'll see one of these. So there are lots of possibilities, but I promise as you get going, it's manageable to keep track of what you have. So really the question here is if x gets really, really, really big, and you can go and use technology to check this. So say x is a million, x is a billion, x is a trillion. You probably don't even have to get that big for these. You want to kind of think about what's happening. So just imagine I'm plugging in a million. So in the top, I'll have 3 million, 1, 2, 3, 4, 5, 6, minus 1. So basically 3 million, right? We're talking about such big numbers that minus 1 hardly has any meaning at all anymore. It barely makes a difference. And in the bottom, you're dividing by a million, 1, 2, 3, 4, 5, 6, minus 1. Again, that minus 1 barely makes a difference. We're basically looking at 3 million over a million, which is going to get very, very, very close to 3. The bigger the number you plug in, the less difference that minus 1 will make, and the closer this will be to 3 over 1. We want to ask this same question for really, really big negative numbers. So now we want to think about what if I plugged in negative a million, and what you'd get is a very similar story. You'd get negative 3 million minus 1 over negative 1 million minus 1. And it turns out the minus 1 makes hardly any difference when we're talking about numbers that big. It absolutely makes a difference when you're plugging in 1 or 2 or 3, but when you're plugging in millions or billions, it's having very little effect on that fraction. So it will still be very close to negative 3 over negative 1, which is y equals 3. So we don't have a slant asymptote, we have a horizontal asymptote. And what's going to be the story here is we always ask that question, what happens when x is really, really big? And what will end up mattering is, are there any powers on x? If so, we need to think really carefully about if the top and bottom don't have the same degree, if the biggest power is different, that will trump any coefficient, like that 3 times x. The 3 won't even matter compared to squaring a million or a billion or a trillion, or cubing a million or a billion or a trillion. So if there are different powers top and bottom, that's all that matters. We don't care about the 3. But if the powers are the same, which is what we're seeing here, we have an x to the 1 on the top and an x to the 1 on the bottom, then it's a story of just what about those coefficients? If that's a million on the top and a million on the bottom, then multiplying by 3 does get interesting. So we'll do lots of practice. I know at first it just kind of seems like magic happening here. I'd like to show a spreadsheet again, and just like last time, I think some people probably won't get a ton just from looking at some numbers, but I think other people might get a little bit of insight from this. So I've already set it up for you. You can see my x value is in the top row, and then the numerator is in a second row, the denominator is in the third row, and then your y value is in the bottom row. And I set up yellow here, this first little rectangle, for what's going on near x equals 1/3, which we said was our 0. And what you can see is that the bottom, nothing very exciting is happening at all. As you move closer to exactly 0.3, the denominator just gets really close to negative 2/3. So we can see it's always negative, and as we move towards the middle, we're just approaching negative 2/3. The numerator is a little bit more interesting. It does approach 0, and this is what we've said. If the top of the fraction becomes 0, it mostly doesn't matter what the bottom is doing, unless it's also 0. That's the one exception. But if the top of the fraction approaches 0, it's going to make the entire thing approach 0. What is a little interesting to see here in terms of the graph is that our y-values switch from negative, I'm sorry, not our y-values, our numerator switches from negative to positive. So to the left of negative 1/3, the numerator and the denominator are both negative, which means our y-values were positive, and then we hit that x-intercept. And because the numerator changed signs, we now have a positive or a negative, so our y-values become positive. So there's that cross right through. So for x-intercepts, we're going to have the same sort of behavior considerations that we did for polynomials. Will it cross straight through? Will it bounce off? And the answer is if there's no power on the numerator or if it's an odd power, you're always going to cross through in some way. You might have a flat spot if it's a cubed or a fifth, but otherwise, if it's just a first power, you will see this cross straight through the axis. The other thing I wanted to look at was x equals 1. I was claiming that we'd get a vertical asymptote, and I just want you to see what's happening there. This one, the numerator isn't terribly interesting, so I'm plugging in x's that are just below 1, so we're getting closer and closer, creeping up to 1, and then on the right side, we're just above 1, so as we work our way in, we're getting closer and closer till we get exactly to 1. So the numerator, you can see it's just always giving me values close to 2. If I plug in exactly 1, I get exactly 2. If I plug in something a little smaller, I get something slightly less than 2. If I plug in something a little bigger than 1, I get something slightly bigger than 2. It's the denominator that gets really interesting. So when I plug in 0, I get 2 divided by 0 is undefined. So this is when it becomes really interesting to ask, well, what's happening really close to 0? And what happens is if you plug in tiny, tiny negative numbers, dividing by a very small number gives you a bigger number. And in this case, we have a positive divided by a negative, so it's giving us a bigger negative number. So when we're close to 0, I get something like negative 17. When we're really close to 0, I get negative 197. You could get even closer to 0 and you'd get an even bigger negative number. That's asymptotic behavior. Your numbers aren't changing very much. We're talking about things that are barely moving over to the right, your x values, but your y values jump dramatically. They skyrocket down toward negative infinity. And on the right, you see the same thing. If you divide by a 0.1, that just moves the decimal place over once. So you get 2.3 divided by 0.1 is 23. But if you get even closer to 0 and divide by 0.01, you get 203 now. And if you plugged in 0.001, I think you'd see probably 2003. And this will just keep getting bigger and bigger as you scoot closer and closer to 0. So our x's are very, very slightly changing, but our y's are very dramatically changing. And that's asymptotic behavior happening. I also wanted to show you that horizontal asymptote so you can see what's happening, sort of what I was talking about there. So here in the middle would be like this is 0. If I plug in bigger and bigger and bigger and bigger negative numbers, you can see that the numerator and the denominator are both getting huge, but they're doing it at about the same rate. So when I divide, it's actually knocking out those zeros for the most part. And you can see I had 2.8, 2.98. 2.998, so on. This is sort of the opposite of our vertical asymptote. Here, we're making massive changes in our x value, and it's making really very small changes in our y value, and that's what's giving us the horizontal asymptote. Whereas on the right side, if our x's go from 10 to 100 to, I did 200s, that one should be 1,000. There we go. Okay, you can see that your numerator is just getting that extra 9 tacked on, and so is your denominator. So yes, they're both growing rapidly, but mostly that divides out and we get 3.2, 3.02, 3.002, and so on. So again, massive changes in x are leading to very small changes in y. That's our horizontal asymptote. All right, to wrap this one up, let's go ahead and sketch it. We do already know what the graph should look like. It should look like that top graph, but let's just see how this would work if we didn't know anything else. I would say I'm going to cross the x-axis at 1/3 0. I have a horizontal asymptote at y equals 3 and a vertical asymptote at x equals 1. So all my local information has really small x values, so I'm not going to make my scale very big. I'm just going to say, okay, that's 0, 1, 2, 3. That should be plenty, and then we'll do like a -1, -2. So a vertical asymptote at x equals 1, again, draw that in. I need to see it or I won't know that you knew it was there. And x-intercept a 0 at 1/3 0, and make sure that's either written carefully on your paper somewhere or that you label it so that I'm not guessing exactly where that was. And then a horizontal asymptote at y equals 3. You absolutely do not have to make your x scale and your y scale the same, so I'll just go like this. Hope I left myself enough room. Okay, so you can absolutely plug in some points to get you started here, but what I know from the global behavior, the horizontal asymptote, is basically there needs to be an arrow really close to that horizontal asymptote as I head out the far left or the far right. And in reality, it might not be quite that close because I'm only going from -2 to 2. These aren't huge x's, but that's what I know. I don't quite know if it needs to go above or below that axis, but it's going to come in really close to that axis. And then I know that I'm only allowed to, other than that, follow the local behavior. So my first piece of local information is that I have to cross right through the axis at 1/3 0. And again, to make this really clear, the reason I know it's a cross right through is because that has a first power. And then my vertical asymptote at x equals 1, it also has a multiplicity 1, which means it's going to behave just like y equals 1 over x, where on the two sides of the asymptote, you see opposite behavior. The signs change. So while we were getting negative values close to the asymptote on the left, we should get big positive values close to the asymptote on the right. If you see right here a squared or a fourth power, you're going to expect the two sides to do the same thing, both sides negative or both sides positive. But when there's an odd power there, it's going to do opposite.